Hi everyone, let's do lesson 10 on measures of relative position. How does a value compare or stack up to the others? For example, let's say that we have a class of 100 students and they take a test. So here is a list of 100 test scores for the class. Let's say you're one of the students. You took that test and you scored 50 points out of 100. Let's say you're here. You scored 50 points out of 100 on the test, 50%. Now, hopefully, the test or the class will not be graded on a straight scale because then 50% is probably an F. If 90% and above is an A, 80% plus is the B, and so forth. So you're hoping that the scores will be curved maybe, or that at least some grading scale other than a straight scale will be used. Then you might be asking yourself, how did you do relative to the class overall? Did you do average typically? Did you do really well? Did you do really poorly? 50% might be great on a physics exam. Well, it might be hard just to look at the sea of numbers, right? So let's try to get a measure for you. And the first thing we're going to do is that we're going to find your z-score. This is your original X score, your actual score on the test, but ultimately we're going to care about your z-score, which basically tells you how many standard deviations above or below the mean you got. If you score at the mean, your z-score is 0. So we want standardized measures, such as a z-score, that will work for practically all populations involving quantitative data. Even with test scores alone, what if you have a test out of 500 possible points or 1,000 points? Maybe it's a very hard exam, like a physics test, where maybe the highest score is 20 points out of 500 points. So let's get a measure of how you did relative to the class, whatever the testing scheme was, whether the maximum possible points were 500 points, 1,000 points, or whatever. Or maybe we're dealing with heights or weights or IQ scores. All right. So z-scores. This formula is the z transformation formula. It will convert from the original raw X score, your actual score on the exam, to the standardized z-score. This idea that we can apply to basically all quantitative data sets, whether you're talking about test scores, heights, weights, ages, light years in space, or whatever. So this formula will convert or transform the original data set of X values into a new data set of z-scores. So we're going to go from a group of X scores to a transformed group of z-scores. And the distribution of the z-scores will have particular properties. The z-scores will tell us how many standard deviations above or below the mean the original X scores are. If you're at the mean, the z-score is 0. So here's what we're going to do. Here is our original data set of raw test scores, the X scores. X of 1 for student number 1. It doesn't matter what order you put the students in, whether it's alphabetical or sorted or whatever, but X of 1 is the test score for student number 1. X of 2 is the raw test score for student number 2. X of 3 is the raw test score for student number 3, and so forth. We're going to transform this X data set into this new transformed Z data set. So each X score gets a corresponding Z score. So what does this transformation do? So we have this original data set of test scores, the original X values. And we're going to plant a flag at the mean. We did this before when we were doing standard deviations, calculating them. But here's the idea. In order to go from the original X scores to the new Z scores, we're going to transform this data set. For one thing, we're going to subtract off the mean. By subtracting off the mean, we're going to ensure that the new mean for the Z data set is going to be 0. So by subtracting off the mean from all the data values, we get a new data set whose new flag is at 0. Again, we applied this idea before when we were computing standard deviations. We recentered the data set so that the new data set has its center at 0. Likewise, we're going to divide the resulting data scores by the standard deviation. This will ensure that the new standard deviation for the Z data set will be 1. So the flagpole, the center, is at 0, and 1 standard deviation for the new transformed data set will be 1. Mean 0, standard deviation 1. Those will be the characteristics of the new transformed Z data set. Again, subtracting the mean from all of the original X values recenters the data so that the new mean will be 0. And we obtain deviations from the mean. So if your deviation was positive 7 points, you scored 7 points above the mean. Dividing by the standard deviation rescales the data set so that the new standard deviation for the Z-scores will be 1. The new sigma will be 1. So if your Z-score is 3, you scored 3 standard deviations above the mean, which would be excellent. So here we have the formulas. If you have a population data set, a population size big N, a Z-score is calculated by taking the raw X score, subtracting off the population mean, mu. You remember is the population mean. And we divide the deviations, those differences, by the population standard deviation. I'll put this in purple. We're dividing by the population standard deviations. We're dividing the deviations from the mean by the population standard deviation. Now, if you have sample size, if you have a sample of size little n, then the Z-score is taken, it's the same idea. You take the original X value, but here you subtract off the sample mean. We have sample data, we subtract off the sample mean. And we divide those deviations from the sample mean by the sample standard deviation, S. But it's the same basic idea whether you're dealing with the population context or the sample context. You take the original data values, the raw data values, subtract off the mean in context, divide by the standard deviation in context. So they both follow this overall format. X minus the mean in context, those deviations by the standard deviation in context. By convention, we round off Z-scores to 2 decimal places because back in the olden days, when we used printed tables, the Z-scores would be written out to 2 decimal places. Although nowadays, with technology, computers, you can round off to more. And remember, Z-scores are very standardized. They have no units. The original raw X scores could be in test points or height in feet, height in inches, weight in pounds, distance in light years. But the Z-scores have no units. The idea being that we can apply this to many different applications involving test scores, heights, weights, whatever, when different units are involved. Now, mathematically, what's happening with the units is that if you take the data values and subtract off the mean, so for example, if you're taking basically test points, something in test points minus something in test points, the deviations are still in test points. But when you divide by the standard deviation, that's also going to be in test points. The idea is that you have something in test points divided by something in test points. The result has no units. Z-scores have no units. It's not in points or meters or feet or whatever. Z-scores have no units. It's a pure raw number, like 0, 2, or negative pi. Z-scores are standardized measures of relative position, how you do relative to the data set overall. So again, if we're studying heights, then we might use inches, feet, meters, light years, whatever, and we'll still obtain the same z-score, whatever the context. So whether you're measuring people in inches, feet, meters, or giants in light years, you'll get the same z-score in terms of the giant's relative position in the group of giants, or your relative position in the classroom.
Okay, any questions?
So, next up, we're going to interpret z-scores.
All right, any questions before we go on? More with z-scores.
Hi, everyone. So you scored 50 points out of 100 on this test. What was your z-score, and how could you interpret that? Well, at the very least, you're hoping that your z-score is positive, because then that would mean that you scored above the mean. So for example, if your z-score were 3, then that means that your raw test score was 3 standard deviations above the mean. In general, if your z-score is positive, then the original raw x score, or x value, was z standard deviations above the mean. Now, if your z-score is 0, then you scored at the mean. You scored the average. If your z-score was negative, then you scored below the mean. You could be sad, maybe very sad. So for example, if your z-score were -3, you did quite poorly relative to the class, because that means that your raw test score, the raw x value, was +3 standard deviations below the mean. In general, if your z-score is negative, then the original raw x score, or x value, was the absolute value of z, standard deviations below the mean. So for example, in example 1, you scored 50 points on that test. Let's say that the mean on the test was 66.9 points, about, and the standard deviation was about 21.4 points. What then was your z-score, and interpret that result? On your calculator, work that out to 2 decimal places. What's your z-score? Right now, you should know what sign your z-score is, right? If the mean overall for the exam was about 67 points for the students overall, and you got 50 points, did you score below the mean, above the mean, or at the mean? You scored below the mean. 50 points is less than 67 points, give or take. So that means that you know your z-score is negative. If you work it out, your z-score was about 50, your raw score, minus the population mean, mu, 66.9 points, all divided by the population standard deviation, 21.4 points. Remember, we had all 100 test scores. We had the full population data set, a census. The z-score turns out to be about negative 0.79. Notice it's negative. You scored below the mean. So that's a check. You scored below the mean. So you know that your z-score was negative. Your z-score is about negative 0.79, which means you scored about 0.79 standard deviations below the mean. So if the scores are curved, if the grades are curved, you may not have failed the test, but you may have gotten a C or a D maybe on the test. But you didn't do too badly. How do you know if you did unusually poorly or unusually well? This is the usual metric. The 2SD rule, or 2 sigma rule, for unusual z-scores. So z-scores that are either less than -2, that's very poorly on the exam, or greater than +2, that's doing very well on the exam. So if z is less than -2 or z is greater than 2, then your z-score would be considered unusual. And the corresponding x values would also be considered unusual. So in other words, data values that are more than 2 standard deviations away from the mean.
Let me pause. It sounds okay. Let's pause. See if the internet can catch up here. Okay, let me try to replay this.
Would be considered unusual. So remember, if you score at the mean, your z-score is 0. Usual or typical values would be between a z-score of -2 and a z-score of +2. That means you'd be scoring within 2 standard deviations of the mean. So again, the typical or usual values would be inside here. But the unusually high scores would correspond to z-scores of greater than 2, and unusually.
Wait, can you understand what's going on here? How bad is it? Okay, I'm pausing. Okay, so let's take a pause again. That's strange. Let me check something. Okay, so right now, follow the captions. I am here, and this is on YouTube. The videos are on YouTube. Go ahead and ask me questions along the way.
Low scores would correspond to z-scores of less than -2. So these would be considered the unusual z-scores, far away from 0. So remember, your z-score is -0.79. Did you do unusually poorly? No, you might not be happy with it, but you did not score unusually poorly. You're here. Now, how would you feel if your instructor told you that the z-score you got for a test was -2.52? How would you feel about that? Probably pretty badly, because you scored unusually poorly. -2.52 would be somewhere over there. Okay, so again, the interval of usual values would correspond to scores within 2 standard deviations of the mean. So let's say hypothetically that the test scores had mean mu equals 50 points, like in our earlier example from lesson 9, and population standard deviation sigma equals 10 points. Then the interval of usual values would be from mu minus 2 sigma, 2 standard deviations below the mean, to mu plus 2 sigma, 2 standard deviations above the mean. So that would be between 30 points and 70 points. This would be our interval of usual values or typical values. So if you scored 30 points, your z-score would be -2. If you scored at 70 points, your z-score would be +2 because you scored 2 standard deviations above the mean. 30 points, on the other hand, was 2 standard deviations below the mean. If you score at the mean, your z-score is 0. So again, for 30 points, that was 2 standard deviations below the mean, z-score is -2. 50 points was at the mean, z-score is 0, not 6, 0. 70 points was 2 standard deviations above the mean, z-score is +2. All right. So going from the x number line to a sort of z number line, okay? The z-score for 30 would be -2, for 40 it would be -1, for 50 it would be 0, for 60 it would be +1, for 70 it would be +2, and so forth. So each x score over here has a corresponding z-score, which tells you whether you're above, below, or at the mean, and how far away from the mean you are in terms of standard deviations, this yardstick. One standard deviation is like a yardstick, a measuring stick. Whether it's 10 points, or maybe 13 pounds, or 5 inches, or 42 light years. One standard deviation is our key measuring stick. Okay, so actually for the list of 100 test scores, I actually did bother to type this out in my Excel spreadsheet. So unsorted, here they are, 70 points, 40 points, 60 points. Maybe these are sorted based on the students' last names in alphabetical order, right? And then the corresponding z-scores, which we obtain by subtracting off the mean and dividing those deviations by the standard deviation. So if you look over here, all the way down here, the mean for the original data set was about 66.9 points. The standard deviation was about 21.4 points, all right? The variation is the square of that. But then when you convert to z-scores, the new mean is 0 and the new standard deviation is 1. So for this column here, for z-scores, the mean is 0 and the standard deviation is 1. Okay, so based on that, what is the interval of usual values? So a student were to ask me, so typically, how do students score on the exam? Based on these parameters. Mu is 66.9 points, sigma is 21.4 points. About. Well, again, the interval of usual values is given from mu minus 2 sigma to mu plus 2 sigma. The score is within 2 standard deviations of the mean. Work it out with a calculator, all right? So the mean, 66.9, minus twice the standard deviation, 21.4. Remember, multiplication precedes subtraction or addition. The result for mu minus 2 sigma is about 24.1 points. For mu plus 2 sigma, it's about 109.7 points. Now, a student might object and say, well, wait a minute. It was impossible to get 109, 110 points on the exam. So it would make sense to truncate that upper limit to 100 points because no one could score above 100 points on the 100-point exam. So that's a technicality. But since this doesn't make sense, we can truncate it at 100 points. So 100 points would be a typical value. You'd feel great, presumably, but still it would be a typical or usual value. It wouldn't be that awesome, sorry, relative to the class overall. It would be like an A+ in the sense that you didn't do that spectacularly better relative to the class overall. Sorry. All right. So think about it. If you scored 50 points on the test, did you score unusually low? Well, your z-score is about negative 0.79. The answer is no. It would not be unusually low. You might be getting a C or a D on the test, but you might not be failing it. However, if you scored 13 points on the test, your z-score was negative 2.52. How should you feel? Probably pretty badly because then you scored unusually low. Yes, by that metric, the 2 sigma or 2SD metric, okay, you scored unusually low. By the way, on the Excel spreadsheet, I had Excel sort these exam scores. This might be more meaningful to you. You'll see that 13 was the lowest score on the exam scored by a student. That was the min. And there was a student who scored 100, the max. And of course, when I sort the data, that does not change the mean, the standard deviation, or the variance relative to the original data set. I'm just reordering the values. If you subtract off the mean, you get the deviations from the mean. So this blue column, notice we have negative values, some positive values, all right? So the person who scored 100 scored 33 points above the mean. The person who scored 13 scored about 54 points below the mean. These deviations average or add up to 0. This is due to rounding error, but it's basically 0. The average of these deviations is 0, but the standard deviation is the same. That's the phase where we basically recenter the data values. All right. We take z-scores. I'm basically sorting the z-scores over here. Okay. So look, the 13 points, that was a z-score of negative 2.52, 2.52 standard deviations below the mean, roughly. That's unusually low. In fact, the 13, the 14, and the 15, all these z-scores were below negative 2. These people scored worse than 2 standard deviations below the mean. So on our number line over here, okay, they were out here in this red zone over here. They scored unusually low. If you scored 28 points, that's not so hot, but that was not unusually low. If you scored 50 points, well, we said you did score 50 points. You scored a bit below the mean, but not too poorly. You scored about 17 points below the mean, about 0.79 standard deviations below the mean, so you scored below the mean, but not too badly. Here, these are people who scored about the mean. Their z-score is about 0. The mean, remember, was about 67 points. Okay. And then we get to the positive z-scores. These people beat the mean, and the person who got 100 points, scored 33 points above the mean, raw, got a z-score of 1.55. But that's only 1.55 standard deviations above the mean. So although this person should feel somewhat proud, this was not unusually high. It was not a spectacularly high score. It's not an outlier by any means. All right, next up, comparing z-scores from different populations.
Any questions before we go on? How's the connection? All right, questions? All right, going on. Comparing z-scores.
Hey everyone, let's say that I go on Maury and I find that I have 2 college-age kids. Wow. So the first thing I do is send them off to statistics class, because I do that. Maybe these are my kids, or thing 1 and thing 2 from Dr. Seuss, I don't know. But let's say that they take these 2 statistics classes and they take different tests, both out of 100 points. So I have a shiny new iPhone I'm going to give to my kid who does relatively better on their exam. Now let's say that both of my kids tell me that they scored 70 points on their first statistics exam. Well, in which of these 2 classes would 70 points be more impressive? Which kid would be more deserving of the new iPhone? And I don't care if you prefer Android. Let's say they want the iPhone. Okay, so let's say that for kid 1, the mean and standard deviation for class 1, which kid 1 is in, had a test mean, mu sub 1, of 55 points, and a standard deviation for test 1 of 5 points. In class 2, where kid 2 is in, let's say that the mean, mu sub 2, was 60 points, and the standard deviation, sigma sub 2, was 10 points. So which kid should get the iPhone? Let's assume that the iPhone is preferable, right? Is a desired item. Let's ask ourselves, which kid deserves the iPhone? In which class is a score of 70 points more impressive? I'll give you 15 seconds to think about this. You can also compute the z-score. Okay, so if you work out the z-score, kid 1 in class 1, if kid 1 got 70 points in that class, we take 70 minus that class mean of 55. So kid 1 scored 15 points above the mean. That's pretty impressive. Dividing by 5. So the z-score was 3. Now, if the kid scores 3 standard deviations above the mean, how well did the kid do relative to the class overall? That kid did extremely well relative to the class overall. This kid did unusually well. 3 standard deviations above the mean, that's an unusually high score. Now in class 2, well, kid 2 did beat the mean, but only by 10 points. 70 minus 60, the class mean for class 2, that deviation was 10 points, but we divide by 10 points. The scores were spread out. So that kid's z-score was only 1, which was 1 standard deviation above the mean. Granted, kid 2 did beat their mean in class 2, but not as impressively as kid 1 did in class 1. So a score of 70 points is more impressive in class 1. In fact, it's unusually high in that class. Kid 1 deserves the new iPhone. And kid 2 can settle for something less. All right. Now, if we assume normality in both classes, we can draw the following pictures. Okay, and then if you're more of a visual person, see, this might be more for the algebra and arithmetic people, but if you're more of a visual person, imagine this. Class 1 had a mean of 55 points and a standard deviation of 5 points. Remember, one interpretation for standard deviation is as the horizontal distance from the mean line to either inflection point, where the graph changes concavity. Again, you don't have to know that, but it's a nice thing to know, right? But notice here that the mean is lower, 55 points, and the scores are more tightly clustered about the mean. The standard deviation was only 5 points. I'll omit the unit here, all right? So the 70 points here was much more impressive. Whereas in class 2, the mean was higher. The mean was at 60 points, and the scores were more spread out. Sigma sub 2 was 10 points. So again, even though kid 2 did beat the mean, the 70 points here wasn't as impressive. One way to look at it is that a higher proportion of students beat kid 2 in class 2 than the proportion of students in class 1 who beat kid 1. In fact, it's quite possible that kid 1 got the highest score. It's unlikely kid 2 did. Okay, next time, more ways of looking at relative position in a data set.
So we'll extend this idea. Any questions? So that's why Z-scores are nice. It's a way of standardizing things. You have class 1, class 2, class 3. Maybe class 3 has a test of 1,000 points, right? Z-scores, it's a way of standardizing. It's like going from, American dollars, Canadian dollars, all to the euro. All right.
Hi, everyone. I just talked about the proportions of students who may have beaten my kids in class 1 and class 2. Now, let's talk about the proportions of students whom my kids may have beaten in class 1 and in class 2. And that takes us to the idea of quantiles. We'll look at 3 types of quantiles, which will help us describe the relative position of data values. So instead of Z-scores, we might think of these quantiles. Percentiles. Think pennies. So think about how a dollar can be broken up into 100 pennies. We can talk about the 25th percentile, the 37th percentile, and so forth. For example, let's say that on a standardized test, you score 85 points on a standardized test. And the report says that you scored at the 92nd percentile. The 92nd percentile. That means that you basically beat about 92% of the other people who took the test. You beat out 92% of the other test scores. So because 92% of the scores lie below 85 points, give or take, we can say that the 92nd percentile of the data is 85 points. P sub 92, that's the notation for the 92nd percentile, is 85 points. Now, there might be issues with rounding and ties, and there are different ways that a computer can compute percentiles. We're not going to get into any of that. Bottom line is, if you score at the 92nd percentile, you've beaten about 92% of the test scores. So overall, you've done well. Now, instead of percentiles, we can think deciles. Think dimes. So the first decile, denoted D sub 1, is just the 10th percentile, just like a dime is worth 10 pennies. Likewise, the second decile, D sub 2, is the 20th percentile. 2 dimes are worth 20 pennies, or 20 cents, and so forth. If you score at the 9th decile, D sub 9, you've done very well. You've beaten about 90% of the test scores. You've scored at the 90th percentile. 9 dimes is 90 cents or 90 pennies. So together, with the minimum score, the lowest score that's achieved, and the maximum score, the highest score that's achieved on the test, the 9 deciles plus these 2 extreme values over here, you can get a list of 11 numbers that describe the distribution of the data. If the deciles are closely clustered together, this often happens in the center. If you have, say, these 3 deciles clustered closer together in the center, that indicates a bump in the data. The idea being that 20% of the data is pretty tightly clustered between here and here. Whereas over here, you had to kind of wait a while to get the 20%. There's kind of a long tail out here. So in addition to percentiles and deciles, in addition to pennies and dimes, what else do we have? We have quarters or quartiles. Think quarters. There are 3 quartiles. The first quartile, Q sub 1, is the 25th percentile, just as 1 quarter is 25 cents. or worth 25 pennies. The second quartile, Q sub 2, is the 50th percentile. Now, this is basically the median, although there could be rounding issues, but just as the median beats about 50% of the test scores, the second quartile beats about 50% of the scores. The second quartile should basically be the median, give or take ties and all that. The third quartile, Q sub 3, is at the 75th percentile. 3/4 is 75 cents. So you've done fairly well. You've beaten about 75% of the class. Now, together with the min, the lowest observed value, and the max, the highest observed value, the first quartile, the median, which is basically Q sub 2, and the third quartile, Q sub 3, form what we call the 5-number summary. This is more efficient than the list of 11 scores if you use deciles together with these. Here we have the 5-number summary. The min score, the max score, and the 3 quartiles, where the second quartile is basically the median. The 5-number summary. So these 5 numbers basically break up the data set into 4 groups of 25% each. So we have a tight cluster over here. 25% of the scores were pretty tightly clustered around here between the median and Q3. This can be represented graphically as a box plot. The 5-number summary can be represented graphically as a box plot or a box and whisker plot. So here's the idea. So the minimum score is indicated by this little tick here. There's a whisker that extends to the box. The box goes from Q sub 1 to Q sub 3. The median is indicated by this line segment here. The median is basically Q sub 2. And then after Q sub 3, there's another whisker that takes you to the maximum score over here, indicated by the little tick. Now, if there are outliers, if you have a test, a physics test, where many people score below 20 points, and you have Albert Einstein here scoring 100 points, sometimes outliers may be separated out as asterisks. And then the maximum is basically the highest realistic score, basically. Right? If the ghost of Albert Einstein is always in your class, then you may have an outlier always out here. And in that sense, we may not want the whisker going all the way to Albert Einstein. Okay. We'll suffice with the highest reasonable student in the class. All right. Now, box plots can be used to compare different populations. Like if you have a box plot for men, another box plot for women, you can do some quick comparisons. So for example, let's take a look at this box plot over here. All right, so what do these 5 scores stand for? We have a box plot for a data set of 100 test scores. And in fact, it's the box plot that comes from the 100 scores I showed you from that big list, from this Excel spreadsheet here. What do these 5 numbers mean? All right, so this left whisker extends to the min score, the 13 points. I'm assuming here there are no outliers. Q sub 1, okay, so that's the min. Q sub 1 is 50 points, the 25th percentile. That beats 25% of the test scores, basically. The median, or Q2, is at 69 points. That beats about half the class. You have about half below, about half above. Q sub 3, the 75th percentile, is 87 points. And you have the whisker leading out to the maximum score. Someone did get 100 points. A box plot, or box and whisker plot, which graphically presents the 5-number summary. The middle 50% of scores are represented by this box going from Q1 to Q3. All right, comparing box plots. So let's say that we have a statistics test in one class and a statistics class, or a statistics test in another class taught by Dr. Evil. Compare these 2 box plots. And address issues of symmetry and skewness also. How do these 2 classes compare? on the test. Okay, let's say that the test scores are out of 100 points. Maybe test one up here in class one, maybe that was an easier test. The scores were generally higher. Whereas here, the median was at 25 points. In class one, also, the scores are more spread out. So what are some things that we observe? Okay, well, in class one, the scores are generally higher, right? And there's greater spread. There's more spread. The scores are more spread out. The range, for example, is 87 points over here. The range over here is only 20 points. Right? And you can tell there's tighter clustering in the second class than the first class. Now, which box plot suggests a symmetric distribution? It looks like this one over here. Okay, because you see here, the median is at 25 points. Oh, this is in red. The median is at 25 points, and looks like the edges of the box and the ends of the whiskers are all symmetric about the 25 points, the median. Whereas here we have some skewness. It looks like there's some skewness to the left. We have a long whisker to the midpoint on the left. So that's just skewness to the left. The distribution for that guy might look something like this. We have a long tail to the left, and the 13 is way over here. Okay, next up, the last measure of spread, the IQR, next time.
Okay, some good observations.
Hi, everyone. For measures of spread, we've had range, standard deviation, variance. Now we have the IQR, the interquartile range, which is Q sub 3 minus Q sub 1. It's the first quartile minus the first quartile. And this here represents the middle 50% of the data. Here, 87 minus 50 points is 37 points. Here, 30 minus 20 points is 10 points. That indicates tighter clustering about the median here. Q3 minus Q1, the width of the box, basically. In fact, one way to define outliers is that an outlier could be said to be more than 1.5 IQRs away from the box, either at the high end or the low end. Here's Albert Einstein. Don't worry, I won't enforce this in this class, but that is one way to define an outlier when you put an asterisk there. Let's take a look at real test data. These are two midterms from a calculus class that I TA'd. First of all, compare the spreads between the two midterms. It looks like the second midterm is more spread out, right? Look here, the standard deviation is 20 points over here, it's 16 points up here, so there's more spread here. Also, look at the IQRs. It's 22 points over here, it's 32 points over here. Stem and leaf plot, a stem plot, lots of scores in the 60s. Here are the high 60s, here are the low 60s.
Vice
We
versa.
have about a bell shape, roughly. We'll do scatter plots later. Box plot. All right, if you look at the box plot for midterm 1 and midterm 2. By the way, this is an ancient version of Minitab, like 1990s. Okay, I don't want to embarrass them. Look here. It looks like for midterm 2, it may have been a harder test. The scores overall were lower. The median was lower. Okay, and for midterm 2, the scores were more spread out. Clearly, the IQR was bigger, right? Okay, here, the IQR was about 32 points as opposed to 22 points over here. Box plots, efficient ways of looking at distributions. So that's chapter 10.
All right. Yeah, I love talking about these things, but we ran out of time. All right. Well, 9:44. Thank you for staying. All right. I'll stick around for questions. And remember, we'll have lots of time for questions on Wednesday. That's really your day. The whole session will be me addressing student questions slowly, calmly. Next Monday's Labor Day. I have the schedule right. Next Monday's Labor Day, the holiday. Then Wednesday, September 9th. Yes, I'll go over the answers, but it'll be very fast. So, do use me on Wednesday, the 2nd, this week. Your homework is due next week, Thursday, September 10th, lessons 1 through 10. Any question? No, correct. So no classes next Monday. It's a holiday. It's a Labor Day holiday. Okay, thank you. So, oh, good question. You know what? I'll offer to record, but I think what might happen is that I think the students might say that they prefer to not be recorded. So I will start by recording, but I'm going to leave it to the students. I'm suspecting that the recording might be short. So it's possible that it might not be recorded for the most part. I'll respect the students' wishes for privacy. In terms of not being recorded, of course, we have the classroom of students on Zoom, right? But I understand if some students feel shy about being recorded. Of course, some students might just say in chat, "Hey, can you do number 3 for me from scratch?" And that's fine. I'm not posting the chats. Oh yes, yes, absolutely. The session on Wednesday, September 9th, I do intend to record that. But the thing is, it is helpful to attend that session by Zoom because if you have questions along the way, like in chat, I can address them in chat. But yes, the Wednesday, September 9th session, I have every intention of recording and posting. In fact, if I forget, I'll do it myself. Okay, there will be a posting of the September 9th session. But you better be prepared. Study, do basically the homework the best you can so that you know what's going on. I'm expecting people to basically know what's going on by that day. Any other questions? All right, I'm still recording. Well, oh yes, oh absolutely. The grade is mostly based on the homeworks. But I am giving you the answers, right? Still, in order to have the context, you need to be studying and, be studying along the way, do the homework along the way. Again, the September 9th session, I'm assuming that you've done the bulk of the homework and you know what's going on. That homework session is not going to be very helpful if you don't know what's going on. But absolutely, you'll be graded. So part of the grade will be an overall scan of how complete it is, and then I will select particular problems to grade, like a sampling. Maybe not entirely random, but I'll grade a selection of problems. All right. That's a very statistical way of grading, right? Take a selection of problems. I don't have time to grade everything, but pick a few problems and look at them carefully. So a sample. Makes sense. A statistical analysis of the homework. Okay, thank you for being with us tonight. Any other questions? I have the recording on. Did anyone want me to stop the recording? Any questions before I stop the recording? Any questions before I stop the recording? I will now stop the recording.